Hi folks! The following video is our second one on rearrangements. I'll be talking about carbanion rearrangements and radical rearrangements. One famous example of a reaction involving a carbanion rearrangement is known as the Favorskii rearrangement. This involves treatment of a molecule with a carbonyl adjacent to an alkyl halide position. This is treated with a strong base, followed by a second step treatment with an acid like hydronium, and the final product is a carboxylic acid. Notice in this particular example, a ring contraction has occurred, so you're going from a 6-membered ring to a 5-membered ring. Somewhat unusual. The mechanism for this reaction involves a first step of a proton transfer rather than a nucleophilic attack of the carbonyl. The hydroxide acts as a base and deprotonates the position alpha to the carbonyl, opposite the position with the bromine attached. This forms a conjugate base, an enolate, where this newly formed carbon lone pair is in resonance with the adjacent carbonyl. The next step of the mechanism is going to be loss of the bromide leaving group, and this is going to be facilitated by a substitution reaction involving that enolate carbon's lone pair. So I'll have two curved arrows, one from the lone pair to the carbon of the alkyl halide, from the carbon-bromine bond to bromine, showing an SN2 type reaction. In this reaction, the carbonyl carbon is untouched, and there's a new bond between the carbon to the left and the right of it. So a strained 3-membered ring has been formed in this intermediate. In the next step of the mechanism, a nucleophilic attack occurs. This time hydroxide serves as a nucleophile to attack the electrophilic carbonyl center. This generates a tetrahedral intermediate with a new carbon OH bond, and the oxygen of the carbonyl is now anionic. This tetrahedral carbon is going to collapse to reform a carbon-oxygen double bond, and a carbon-carbon bond is going to break simultaneously. So I would bring down a lone pair from the anionic oxygen, and break a carbon-carbon bond and use it to form a carbon lone pair at the neighboring position. This step reforms the carbonyl of what is now a carboxylic acid, and it broke a 3-membered ring, retaining the 5-membered ring. The position adjacent to the carboxylic acid is an anionic carbon. And the next step of the mechanism is going to be protonation of this anionic carbon to generate a temporarily neutral intermediate. In the earlier proton transfer step, an equivalent of water was formed, so I'll use the carbon anion as the base to deprotonate water, since I'm under basic conditions. This temporarily generates a neutral carboxylic acid. But because the carboxylic acid is fairly acidic and the reaction is taking place under basic conditions, you can assume that there's an excess of hydroxide around. A deprotonation will occur. So the hydroxide will deprotonate that carboxylic acid position. This generates a carboxylate anion, and this is the form of the molecule that will be present until H3O+ is added in the second step. Once H3O+ has been added, a proton transfer can occur using the anionic oxygen as the base, and H3O+ is a strong enough acid to protonate the carboxylate anion, getting to the neutral carboxylic acid product. So a couple of steps in this mechanism are somewhat unusual. I'd say the first one is this intramolecular nucleophilic attack to generate a 3-membered ring. And then the second unusual step is breaking a carbon-carbon bond and forming a carbanion in the loss of leaving group step. That forms the carbonyl again. The fact that a carbon anion is generated is okay because this is occurring under basic conditions, So this can temporarily be formed and quickly protonated by water. Carbanions can also undergo concerted rearrangements if they're the appropriate position away from an alkene. So in this case, a carbanion is present, separated from an alkene by 2 carbons. A rearrangement reaction can occur, where I will take the carbon lone pair to the end carbon of the alkene, move the pi bond, and break a carbon-carbon bond to form a lone pair. So this formed a new carbon-carbon bond, which is this one in the products. The pi bond has moved, and a carbon-carbon sigma bond broke, and those electrons were used to form the new carbanion in the products. So this reaction is not super common, and it relies on this really appropriate positioning of the carbanion relative to an alkene. Another type of rearrangement that can occur is if you have a carbanion that is one position away from an alkene. What's observed is that if you have a carbon-13 label at this carbanion position, it will scramble into the CH2 position as well. So this equilibrium requires some sort of rearrangement to occur. The mechanism for this reaction is going to involve an addition of the anionic carbon to the alkene in the first step. So I will take the lone pair to the closer carbon of the alkene, take the pi bond to the end carbon to make a new lone pair. This temporarily generates a 3-membered ring, and the carbon coming off of it, a CH2 group, is now anionic, temporarily in this intermediate. In order to get to the product where the carbon-13 group is at the CH2 position instead of the anionic position, I'm going to reform the alkene, but I'll break the other carbon-carbon bond of the 3-membered ring. So I'll have 2 curved arrows again, one bringing the lone pair down, and now I'm going to break the carbon-carbon bond to the carbon that is not the carbon-13 position. And this second step would generate that other carbanion product. So in this mechanism, the anionic carbon and the CH2 position change places, and you have an equilibrium between these 2 forms of the anionic molecule. In order to go back and forth between these, a 3-membered ring intermediate with an adjacent carbanion is present. Rearrangement reactions will also commonly involve radicals as well. One common type of radical rearrangement is a hydrogen shift. So I'm being intentionally vague here. You have some sort of carbon radical in a molecule with a CH bond at a position further away from it. A radical hydrogen shift will involve 3 curved arrows, one from the radical to a point in space, one from the CH bond to the same point in space, and one from the CH bond to the carbon. This hydrogen shift generates a new carbon-hydrogen bond as well as a new radical. And the positions of these, the CH bond and the radical, have simply changed with each other. In terms of the terminology for these hydrogen shifts, these are going to be defined by the distance between the original and the newly formed radical centers. One common type of hydrogen shift is a 1-3 shift. In terms of numbering, you number from the carbon radical to the CH bond, and then you would draw the 3 curved arrows. From the radical to a point in space, from the CH bond to the same point in space, and from the CH bond to carbon. This creates a new CH bond at the original 1 position, and a new radical is created at carbon 3. Another common type of hydrogen shift is a 1-5 shift. Here as well, you would want to number from 1 being the radical center to 5, your 5 position, and then draw out a CH bond at this position. You draw 3 curved arrows for the hydrogen shift, from the radical to a point in space, from the CH bond to the same point in space, and from the CH bond to the carbon. This 1,5 shift would generate a new carbon-hydrogen bond at position 1 and a new radical at position 5. Radicals are very reactive, and these 1,5 shifts are particularly prevalent, but you can also have radical shifts involving other positions of CH bonds as well. One mechanism in which a 1,5 shift occurs is known as the Barton reaction. This is a rearrangement where you start out with an NO2 group at one end of a molecule, and upon treatment with light, this position is turned into an alcohol group, and the NO group is added at a position 5 away from this. So notice in order to install this new NO group, a CH bond had to break at this position, and that hydrogen is now attached to oxygen. The first step of this mechanism, which is aided by light, is a homolytic cleavage event. This is going to break the weakest bond in the molecule, the nitrogen-oxygen single bond. So I'd use 2 curved arrows, breaking that bond and distributing the electrons from that bond evenly between nitrogen and oxygen. This generates an NO radical molecule and an oxygen radical. The oxygen radical molecule is going to undergo a 1,5 hydrogen shift. I would number the positions from the oxygen radical to carbon 5, then draw out a CH bond at this position, and then draw the 3 curved arrows for the hydrogen shift. 2 meeting in space and 1 going to carbon at the 5 position. This generates a new OH bond and a carbon radical at the 5 position. And to form the final carbon-nitrogen bond of the product, you could have a coupling reaction between the carbon radical and the NO radical. So you could bring these 2 radicals together, and this would generate that final carbon-nitrogen bond of the product. So this is a pretty cool reaction. We typically think of CH bonds for sp3 hybridized carbons as being unreactive, but in this radical reaction, you're able to get a shift to occur in order to generate a carbon radical, leading to a functionalization with a new nitrogen group in the product. And this reaction is specific for the 1,5 shift. Another type of rearrangement involving radicals are shifts of vinyl or aryl groups. These shifts are going to involve intramolecular radical addition to a pi bond, followed by an elimination reaction to regenerate a radical. What's experimentally observed is that if you have a radical separated from an alkene by one CH2 group, this radical is undergoing rearrangements that change the positions of this carbon and that of the CH2 group, similar to what we saw for the Carbanion earlier in this video. So if you labeled this radical position with a carbon-13 group, what you would observe is you would end up with carbon-13 scrambling in both this radical position as well as the CH2 position adjacent to it. In order to scramble these 2 positions, this carbon radical is going to add to the alkene to generate a 3-membered ring temporarily. So I would bring the radical to a point in space, take 1 electron from the pi bond to the same point, and take the other electron from the pi bond to the end carbon. This would temporarily generate a new carbon-carbon bond, forming a 3-membered ring. And the CH2 group coming off of this is a new radical. In order to form the product where the carbon-13 is the CH2 position without the radical, what you would do is you would reform the alkene and break the other carbon-carbon bond of the 3-membered ring instead. So this will have 3 curved arrows as well, 1 from the radical coming down, one from the carbon-carbon bond adjacent to it coming over to form the pi bond, and one from that same carbon-carbon bond going over to form a new radical. So breaking this carbon-carbon bond of the three-membered ring would generate the product where you have the carbon-13 in the CH2 group between the radical and the alkene. So you can think about this rearrangement reaction as converting rapidly between the two forms of the radical with different positions of the carbon-13 center, and these would be in equilibrium with each other. A similar type of equilibrium occurs if you have a radical separated from an aromatic ring by a CH2 group. If you started out with a carbon-13 at this radical position, what you would find is it would quickly establish an equilibrium where that carbon-13 is at the CH2 group between the radical and the phenyl ring as well. And a similar mechanism goes back and forth between these two radical forms as well. Here as well, the first step of the mechanism is going to be taking the radical and using it to add to the alkene to temporarily generate a three-membered ring. I would take the radical electron to a point in space, take one electron from the pi bond to the same point in space, and the other electron from the pi bond to the adjacent carbon. The two curved arrows coming together show the formation of the new three-membered ring, and a new radical is generated adjacent to this three-membered ring. I'm not going to draw them out here, but notice that this new radical that was generated is adjacent to an alkene and another alkene, similar to like an aromatic substitution reaction, so there are more resonance forms of this radical as well, I just haven't drawn them out here. In order to get to the product where the carbon-13 is in between the phenyl group and the radical center, I'm going to reform the pi bond and form the radical at the non-labeled carbon instead of the CH3 carbon. So to do this, I would take the radical down to start to form the pi bond, break this carbon-carbon bond, and use the electron to form the pi bond, and take the other electron from the carbon-carbon bond over to that carbon that's not labeled. This would break the three-membered ring, restore aromaticity of the phenyl group, and it would switch the positions of the labeled and unlabeled carbons while regenerating the radical. Okay, so this video talked about carbanion rearrangements as well as radical rearrangements. One carbanion rearrangement reaction was the Favorskii reaction that involved conversion of a ketone adjacent to an alkyl halide starting material into a smaller ring containing a carboxylic acid. And I also showed you examples where carbanions that are adjacent to alkenes can undergo rearrangement reactions as well. In terms of radical rearrangements, radicals undergo hydrogen shifts quite readily, and this appeared in the Barton reaction. And I also showed you some examples known as vinyl and aryl shifts, where radicals that are separated from alkenes or aromatic rings by a single carbon undergo these interesting rearrangements that proceed by a strained three-membered ring intermediate. That's it for this video. I will see you in class.